Okay, today we are going to do wave theory of light. That light travels in the form of waves. Christian Huygens was a Dutch physicist and he proposed that light has wave nature. And it could very well explain the then known phenomena of refraction, reflection and rectilinear propagation of light. So it was in 1678 that he proposed the wave theory of light. But it was under a very much debate because in that era Sir Isaac Newton in 1675 has already proposed the corpuscular nature of light. What does it say? That light travels in the form of stream of particles emitted by a light source. There was a debate that if light has a wave nature, then it should bend around the obstacles and we should be able to see beyond the obstacles. If light travels in the form of waves, then it should bend around the obstacles, which was later on found to be correct by the theory of diffraction. So because of Sir Isaac Newton's stature at that time, his corpuscular nature of light remained predominant. Later on, it was in 1827 and not before that when Thomas Young gave his double slit experiment on interference and Fresnel's diffraction pattern given by Fresnel's, that we came to know that light travels in the form of waves. Okay, later in 1873, Maxwell gave the electromagnetic theory of light, that light travels in the form of electromagnetic waves. He demonstrated an experiment with electrical oscillations in a circuit and where electric field and magnetic field propagate in space in mutually perpendicular direction and perpendicular to the direction of propagation. So electromagnetic waves are of short wavelength are light waves and they travel with the speed of light. Later on, electromagnetic waves, however, failed to account for the phenomena of photoelectric emission given by Albert Einstein in 1905. He said that light, what is Einstein's photoelectric emission? That light, instead of being distributed as electric and magnetic field through space, is concentrated in small packets of energy called photons, where the energy of a photon is directly proportional to its frequency. Okay, and this Einstein's photoelectric emission, that when light falls on the surface of a conductor, electrons are ejected from the surface. This which considered that lights are made up of packets of energy called photons. Okay, Einstein's photon nature of light has a striking confirmation by Compton's theory, which says that, or Compton's experiment rather, Compton effect, we call it Compton effect, which says that when the photon strikes an electron, then there is a conservation of momentum and kinetic energy before and after collision. Means the momentum and the kinetic energy remains the same before and after collision. So now today the physicists believe in the dualistic nature of light, a dual nature of light. That light shows both the nature of its wave nature, which prove the phenomena of interference, diffraction, polarization, and its particle nature, that is corpuscular nature, which proves the interaction of light with matter, like photoelectric effect, Compton effect. Okay, now we are going to do Huygens wave theory. Huygens considered light travels in the form of waves, but he considered light as mechanical waves. Light he considered as mechanical waves. What are mechanical waves? They require a medium for its propagation. Now the question arises that if mechanical waves, they require medium for its propagation. Now the question arises, if light requires a medium for its propagation, then how light from sun reaches the earth so quickly? Or how does light from sun reaches the earth if there is nothing in between? So it was then all the physicists over the world considered that there is all over the universe an all-pervading ether medium. It was this ether theory that was considered at that time, an all-pervading ether medium everywhere. Now, what is this ether medium? If there is a medium, then how come, again there was a debate, how come this light from sun to earth covered a distance of 173 million kilometers in 8 minutes 20 seconds? In such a small time, how can it cover such a large distance? So it was considered that this ether medium has a large elasticity. The elasticity is large and elasticity is huge, and its density is very low. Okay, it's a less dense medium, and its elasticity of the medium is very high. What do you mean by elasticity of a medium being high? That it is elasticity means it is a measure of its restoring force, of the medium to return to its original shape after the deforming force is removed. So after the light has passed that particular portion of the medium will regain its original shape. So the elasticity of the medium is very high and the density is very low. Now velocity of a wave is given by elasticity divided by density. So if density is low, this becomes high. If elasticity is high, this becomes high. So the speed of the light is huge, which makes it, so it takes only 8 minutes 20 seconds to reach from sun to earth. It makes the speed of the light huge, elasticity being high and the density being low. It's a less dense medium. This is the characteristics of this ether medium that was considered at that time. Okay. Next, we are going to learn about wavefront. Now, according to Huygens' theory, a point source sent out waves in all directions, equally in all directions in space. So we are going to write down certain points. A point source S, say S is the point source, it sends out waves equally in all directions. In space. Okay, so the point source is sending out waves equally in all directions in space. Mind it, it's the 3D space. Okay, space means 3D surface. Okay, in all directions it is spreading out the waves. Okay, second, if v be the speed of the wave, if v be the speed of the light wave in that medium in which the light source is kept, if v be the speed of the light wave, v is the speed of the light wave in that medium, then after a time t naught, the waves of light will travel a distance. The waves of light will travel a distance. You tell me what distance it will travel. if v is the speed of light in that medium and t naught is the time, then in a time t naught, the wave will cover a distance, velocity into time, that will give you distance, speed into time, so it will cover a distance v t naught. This is the distance it will cover. Now third point is, say this is v t naught. The wave has covered this distance. Now all the points where the waves have reached, in the same time t naught are on the surface of a sphere. Okay, in this page it is on the surface of a circle, but actually it is on the surface of a sphere because the waves are being propagated equally in all directions in space, not in this page of paper. Okay, so all the points where the waves have reached are on the surface in time t naught, of course. In time t naught, all the points where the waves had reached are on the surface of a sphere with S as center and v t naught as radius. So you may write down all the points where the waves have reached in time t naught are on the surface of a sphere with S as center and v t naught as radius. The fourth point is, since all the points on the surface of the sphere have received the waves in the same time t naught, all points on the surface of this sphere, okay, there will be a sphere, okay, all the points where the waves have reached the same time t naught, in the same time t naught, all the points are on the surface of a sphere. Okay, if you draw a sphere, all the points will be on the surface of a sphere. Okay, because each wave has covered a distance v t naught equal in all directions in space. So you can only draw a sphere for this distance covered for a point source. Now since all the points on this sphere have received the waves, all the points on the surface of this sphere have received the waves at the same time t naught. At the same time t naught, all the points on the surface of this sphere have received the waves. Therefore, all these points are in the same phase of oscillations, or they are vibrating in the same phase. All the points on the surface of this sphere, this point, this point, this point, this point, have received the waves after the same time t naught. After the same time t naught, this point has received the waves after time t naught, covering a distance v t naught. This point has received the wave after a time t naught, covering a distance v t naught. This point has received the wave after a time t naught, covering a distance v t naught. Okay, so the distance is the same. So for all these points, the waves over here are in the same phase of oscillation. Because what is the equation of a wave? A sine omega t plus kx. That omega is the frequency of the wave. It depends upon the source. Okay, it depends upon the source. The frequency of the wave depends upon the source. It will remain the same for all the points. Okay, so for this point, say y1 equal to a1, and this is the phase. K is the wave number. Okay, the wavelength. So for a point source, the wavelength is the same, and x is the distance covered, vt naught. Okay, K is equal to 2 pi by lambda. For a monochromatic light, it will have the same wavelength. Okay, and x is the distance covered by the wave. So this phase will remain the same. Again, y2 equal to a2 sine, again omega t plus kx vt naught. So the phase is remaining the same because the distance covered is the same. The term attached with the sine function gives you the phase. So phase is the same because the distance covered is the same. So all the waves are in the same phase of oscillation. Okay, all the points, what did I say? All the points on the surface of this sphere have received the waves after a time t0, and they are in the same phase of oscillation, or vibrating. The points are vibrating in the same phase. So what is the fourth point? All the points on the surface of the sphere have received the waves after a time t0. So all the points are vibrating in the same phase. All the points on the surface of a sphere. So these points on the surface of a sphere have received the waves and they are vibrating in the same phase. So this surface of the sphere where all the points are vibrating, or all the particles of the medium are vibrating in the same phase. Okay, this surface of the medium is called a wavefront. This surface of the medium is called a wavefront. So how do you define wavefront? Wavefront is a surface in a medium such that the medium particles, you define it as wavefront as a surface in a medium such that the medium particles lying on the surface are in the same phase of oscillation. Their phases will be the same. Okay, so wavefront is a surface in a medium such that the medium particles lying on the surface are in the same phase of oscillation. Okay. Now, another property is that a line drawn perpendicular to a wavefront, is called the ray of light. A line drawn perpendicular to a wavefront. What is the perpendicular to a sphere? A perpendicular to a spherical surface always passes through its center. We know that. So a line drawn perpendicular to this wavefront, this spherical surface, will pass through its center and is the radii. So the radii of all spherical, all the radii of this spherical wavefronts, all the radii are the rays, represent the rays of light. I once again repeat, or you may write down the point, that a line drawn perpendicular to a wavefront, where shall I write it? Shall I write it here? That is the sixth point. A line drawn perpendicular to a wavefront represents a ray of light. So all radii of the spherical wavefront represent rays. Okay, so we have learned about wavefront. And we have learned about the rays of light. The rays of light are perpendicular to a wavefront, to a spherical wavefront. The rays of light are perpendicular to spherical wavefront. So we know now what you mean by a wavefront. In brief, I just repeat, you have a point source of light which is giving out waves in all directions. In time t0, if v be the speed of the light in that medium, then it is traveling a distance v t0. And all the points where the waves have reached in time t0 lie on the surface of a sphere with S as center and Vt naught as radius. Okay, all the points where the waves have reached in time t naught lie on the surface of a sphere with S as center and Vt naught as radius. And since all the points on the surface of the sphere are received the waves after the same time t naught, okay, these all points are vibrating in the same phase. They have received the waves after the same time t and they have covered the same distance x. So they are vibrating in the same phase. Okay. So this surface is called a wavefront. All points on this surface are vibrating in the same phase. So this surface is called a wavefront. So wavefront is a surface in a medium such that the medium particles lying on the surface are in the same phase of oscillation. A line drawn perpendicular to the wavefront or perpendicular to the surface of the sphere give a ray of light or the direction of propagation of the ray. Another important point is that the secondary wavelets, or rather you can say the backward wavefront. Okay, we'll come to that. I just don't want to say it now. We are going to make the following assumptions of Huygen's wave theory. Assumptions of Huygen's wave theory. Now, what are the following assumptions in Huygen's wave theory? In a homogeneous and isotropic medium, Christian Huygens made the following assumptions. That when light travels in a homogeneous and isotropic medium in the form of waves, then what assumptions he has made? What do you mean by homogeneous and isotropic medium? Homogeneous medium means that the properties of the medium are same all over. They consist of same type of molecules. You know the meaning of homogeneous medium. Isotropic medium means the velocity of light or the refractive index of the medium is same in all directions. That is the meaning of isotropic medium. Okay, so in homogeneous and isotropic medium, which light is to be propagated, then Huygens in the form of waves, then Christian Huygens made the following assumptions. What is the first assumption? That each point on the wavefront act as a source of fresh disturbance, okay, called secondary wavelets. So the first assumption is each point on the wavefront act as a source of fresh disturbance called secondary wavelets. The second point is this wavelet spread out in the medium. This wavelets, each point is a source of secondary wavelets. Okay, this wavelet spread in the medium with the velocity of light in that medium. All points on the surface of a wavefront act as a fresh source of disturbance called secondary wavelets, and this secondary wavelets, okay, there are spherical disturbances in the medium, and this secondary wavelets spread out in that medium with the velocity of light in the medium. So the second point is that this secondary wavelets, this is all theory based until we reach the reflection of light at a plane surface where we can do some derivation. So this secondary wavelets and this assumptions of Huygens wave theory is very important. So this secondary wavelets travel in a medium, spread out in the medium, with the speed of light in that medium. And the third point is the new wavefront at a later instant is obtained by taking the new wavefront at a later instant. How do you get the new wavefront at a later instant? it is obtained, these are the secondary wavelets, and if they have traveled a distance delta t with a speed v, then they have covered a distance v delta t. So the new wavefront at a later instant delta t is obtained by taking a forward envelope of the secondary wavelets at that instant. Okay, forward envelope of the secondary wavelets at that instant. Okay, it has covered a distance of v delta t in time delta t. Okay, so the next or the new wavefront is obtained by taking the forward envelope of the secondary wavelets. These are the points of the secondary wavelets. Okay, so these are the secondary wavelets traveling a distance of v delta t. So the new wavefront is obtained by taking a forward envelope of the secondary wavelets at that instant. New wavefront at a later instant is obtained by taking the forward envelope of the secondary wavelets at that instant or at that time. Okay, so this is the assumptions of Huygen's wave theory, and he has better explained it as by showing that a spherical wavefront advances as a spherical wavefront. So he has taken a trace of a spherical wavefront AB. This is the point source S, which is giving out point source of light, which is giving out waves in all directions, equally in all directions in space. In a homogeneous and isotropic, this point source S is kept in a homogeneous and isotropic medium. Now AB is a trace of spherical wavefront at any instant t0. Say at any instant t0. Now each point on this wavefront act as a source of secondary wavelets. Isn't it? That is the assumption of Huygen's wave theory. Say this is point A, this is point B, this is point C, this is point D. So each point on this wavefront acts as a source of secondary wavelets. Now starting from different points on the wavefront at the instant t0, the secondary wavelets will reach a distance, say v delta t, in time delta t. Okay, in time delta t it will reach a distance v delta t. So it will cover a sphere. The secondary wavelets will be a sphere, or secondary disturbances will be a sphere, will be in the form of a sphere. The waves will propagate in all directions in space, right? The secondary wavelets from this point has covered a distance v delta t in all directions in space. So the spherical disturbance of this secondary wavelets will be a sphere with A as center and v delta t as radius. Okay, similarly here it was covering a v delta t. Over here it is again the secondary wavelet starting from the point C will cover a distance v delta t with C at center and v delta t as radius. Okay, now so the forward envelope to this secondary disturbances or to this secondary wavelets after a time delta t. Okay, after a time delta t, the forward envelope to this secondary, because these are the secondary wavelets advancing in the medium. Okay, from the points A, B, C, D, from these points on the wavefront, these are the secondary wavelets advancing in the medium. So the envelope of this secondary wavelets after a time delta t will give you the new wavefront, which is also a spherical wavefront. So a spherical wavefront advances as a spherical wavefront. Now it can be shown that the backward envelope or the backward wavefront has an intensity 0 or an amplitude 0. Now it happens when you drop a rock in a small rock in a pond. Okay, there are ripples and the spherical disturbances advances, and the wavefront, the backward wavefront, keeps on dying out, and the wavefront advances in the medium. Okay, so this is the same way the backward, it can be shown that the backward wavefront advances in backward wavefront has 0 intensity or 0 amplitude. Okay, Now, Huygen's wave theory can explain the reflection of a plane wave at a plane surface. So, we'll be doing this. Okay, for a point source, a wavefront is a spherical wavefront. If the light rays are coming from infinity, then they are parallel rays. For parallel rays or parallel waves, the wavefront is a plane wavefront. Okay, it's a plane wavefront. So these are very important points. For a point source, the wavefront is a spherical wavefront. For parallel rays or the rays coming from infinity, the wavefront is a plane wavefront. And for a line source of light or linear source of light, the wavefront is a cylindrical wavefront. Okay, with the linear source of light as its axis. Okay.